Hello, my name is Brian McCoy. I'm an applications engineer at ON Semiconductor. I am in the AC to DC group, and I'm here to talk to you today about the NCP1568, which is an active clamp flyback converter. The active clamp flyback converter can be used to increase the power density of universal AC power inputs to DC outputs. The NCP1568 is suitable for all types of charging, including industrial, telecom, and consumer. We'll go over some of the major features today, including control scheme, adaptive ZVS frequency modulation, which allows us to adapt to variable output voltage, integrative adaptive dead time, peak current mode control, light load operation including DCM and skip mode, the transition between DCM and ACF, and minimum operating frequency of 31 kHz. Our part also has quiet skip, which eliminates audible noise, allowing us to have a standby power of less than 30 milliwatts. We also have an integrated JFET 700 volt startup and integrated sensing for the switch node. The same JFET also allows us to do brownout and X2 discharge. This is a typical application diagram for active clamp flyback. The three critical components for this topology are NCP1568, which is an active clamp flyback controller, the NCP51530, which is a 700 volt half-bridge driver, and the NCP4305, a secondary side synchronous rectifier. Together, these three ICs make a topology operate harmoniously. The traditional flyback is a workhorse of the industry, accounting for the majority of adapters. The converter is simple as it has a single ground-based switch. Unfortunately, it suffers from switching losses which increase with frequency. As the frequency losses increase due to hard switching or transformer leakage, which creates excess energy that must be clamped and dissipated, improvements to the flyback topology have been made and introduced in the quasi-resonant flyback converter, which uses valley switching to minimize the losses in the flyback converter. However, it does not minimize the losses due to leakage ringing, and the energy must still be dissipated, limiting the maximum frequency that the quasi-resonant converter can operate at. The next evolution, our active clamp flyback converter. This converter recycles leakage energy with one additional switch on the primary side and is used to achieve 0 volt switching. This active clamp flyback minimizes two sources of energy and allows it to switch at a higher switching frequency while maintaining a better or the same efficiency. ON Semiconductor has created an IC that controls the active clamp flyback resonant converter along with a proprietary 0 volt switching or ZVS switching based frequency modulation to achieve very high efficiency, high density designs while meeting COC Tier 2 4-point efficiency requirements while balancing standby power requirements. Before we can discuss the IC operation, 4 critical pins need to be discussed: the RT pin, the CS pin, the SW pin, and the FB pin. The RT pin is used first to set the maximum DCM operating frequency. Second, it is used to set the minimum and maximum ACF operating frequency. And finally, to set the peak currents in frozen peak operation at light loads. The FB pin is used as an analog input for the primary side to regulate the output voltage using peak current mode control. The CS pin senses the main switch current. And finally, the SW pin is used in ACF mode to monitor the rising and falling of the switch node. In this slide, we show the soft start. During T2, the boot capacitor is charged. To charge the boot capacitor, we keep the on time very small for the low side drive. We also keep the switching frequency very low and a minimum of 5 pulses. To minimize energy during shoot through, we also keep the switching frequency low. This keeps the average energy very low. The DCM operation is maintained for T3. During T3, we also charge the boot capacitor. Once the boot capacitor is charged, we allow for high side startup. We phase in the high side drive during T4 time, gradually increasing the energy transfer to the secondary side from the ACF clamp capacitor, which provides less stress on the MOSFETs. We then extend the ACF operation into T5. After we have completed the soft start, we stay in active clamp flyback for quite some time. This is a natural state, as when you're turning on into heavy loads and turning on into capacitive loads. This slide shows a typical startup sequence that we just described. We will now explore operating modes of the NCP 1568 to see firsthand how great standby power can be balanced with outstanding full load efficiency. First, we will discuss skip or burst mode operation. At light loads and no loads, the NCP 1568 operates in DCM mode of operation with a fixed peak current. The lowest operating frequency in DCM mode of operation is 31 kHz. To maintain regulation on the converter, it periodically switches off into a low power state between 31 kHz and then applies burst pulses. This enables low standby power, as we can see. I'm going to go ahead and turn this on for you. I'm going to go ahead and move my time base out here, but what we can see is that our power is decreasing below 20 milliwatts of standby power, which is less than 1/3 of the 70 milliwatt COC Tier 2 limit. As we increase the load, the DCM or dead time decreases. Our frequency will keep increasing. As we further increase the load in DCM mode, we see the frequency keeps going up. We increase until we hit the 1/2 of the RT program frequency. Typically for variable output voltage programming protocols such as USB PD and Qualcomm Quick Charge, we see that over various output voltages, the most efficient operating point is DCM mode for light load up to 25%. After 25% load, we operate in active clamp mode. In this slide, we're showing how as feedback voltage moves up, the frequency is modulated with an inbuilt VCO, and we can move all the way up to F divided by 2, or RT divided by 2, as mentioned previously. The NCP 1568 has a dedicated pin, ATH, to allow the designer to set the optimal DCM to ACF transition point. Further, an additional pin, DTH, is provided to allow the designer to adjust the point at which the IC transitions from ACF to DCM. The freedom to adjust both thresholds allows the designer to optimize any system to their desired specification. We're going to go ahead and take a look at one of those transitions now. We're operating in DCM mode, and I'm going to go ahead and increase the load, and now we're operating in ACF mode. It was just that easy. Once the designer selects a transition point, the NCP 1568 enters and exits ACF mode using leading edge modulation, or LEM. The LEM slowly phases in the high side drive pulses, allowing the switch node to achieve 0 volt switching while slowly moving a large amount of energy from our clamp capacitor from the primary side to the output of the secondary side. The LEM is completed in 0.5 milliseconds, and after completion, the power supply is operating in active clamp mode. Here we can see the real-time increase of the high side drive pulses to increase the leading edge modulation drive time, so that when we are done, we are completely in ACF mode. The transition from DCM to ACF and ACF to DCM is governed by the feedback voltage. The NCP 1568 has an integrated high voltage JFET that allows the observation of the switch node directly, reducing phase lag associated with other methods. When the high side driver is shut off, a time reference is started and the switch node is monitored to determine when it falls below 10 volts. If the switch node falls faster than the time reference, the negative current is large and the frequency should be increased to reduce the negative current. If the switch node falls slower than the time reference, then the negative current is small and the frequency should be decreased to reduce negative current. In this way, the frequency of the converter is modulated to minimize negative currents for line, load, and output voltage, optimizing efficiency for all operating conditions. We can see that the negative current is minimized when the feature is engaged. The negative current is minimized over load conditions. I'm going to go ahead and move my load up here a little bit, and we're going to see how the negative current is modulated and the frequency is modulated with our load change. So I'm going to go ahead and move that load up. And it's really subtle because this is at 5 volts. but you can see that the frequency is increasing and decreasing. And if I go far enough, it'll shut off. But if I go far enough, we'll transition to DCM. This is the frequency plot of the USB PD voltage range, showing the frequency change as the load is increased. The yellow region is ACF operation and the green region is DCM operation. We can see as we zoom in, the time modulation is always updating, giving us a natural spread spectrum behavior. Further, we can see that as soon as the switch node falls to 12 volts, the low side drive turns on due to the adaptive dead time control. I'm going to move the load here a little bit so you can see as I increase the load, that time is modulating slightly. It's a little bit tough to see, but that's because the control mechanism is so good. The adaptive dead time control reacts in less than 30 nanoseconds. But if ZVS does not occur, the IC is equipped with a maximum dead time of 400 to 600 nanoseconds to ensure smooth operation. This demonstration board, our standard demonstration board, has a CC/CV control board on it, which allows the user to check different output voltages, flipping these switches, and distinguishing between the powertrain operation and the protocol operation. So because we have a CC/CV controller, once the designer is comfortable with the behavior of the active clamp flyback controller, any protocol chip can be pushed into this slot using just 6 simple connections. The results of the USB PD protocol compared against the COC Tier 2 limits is shown here. The designer has good margins in order to optimize efficiency or cost. I've shown you our standard demonstration board today and we've walked through some of its features. However, I would like to show you our high density board here. This is a 65 watt USB PD adapter. This adapter is fully compliant to COC Tier 2 and passes EMI requirements. This design is 31 watts per cubic inch and has an RM8 LP core. Thank you for joining me on this brief look at some of the major features of the NCP 1568. For more information, please visit our website.